Okay, so this is the back of the napkin assignment. My name is Matt, and I'm going to be going over big O notation for computer science. So to get us started real quick, big O notation looks something like this. We have an O and some kind of function inside. We'll call it g of n. Okay, now the typical thing of big O notation is that it describes the time it takes for a computer science algorithm to complete compared to the size of the input. So we can just kind of represent this as size and time. There are three cases for this. We're going to go over them. And this is kind of how calculus can relate to it. So we have three cases, and the calculus part is that we take the limit as n approaches infinity, where n is the size of the set. And we look at the ratio of f of n, a function we're interested in, compared to g of n, a function we're testing. And this will give us three cases we're interested in. One, when we evaluate this left-hand side of the equation, we might end up with a 0. And this tells us that the bottom is growing quicker than the top. And this will show us that f of n has a smaller runtime than g of n. We can end up with a constant case, and this will tell us that f of n has O g of n. And we can have an infinite case, and this is the case that g of n is less than f of n. So these are kind of our three cases, and at first they don't seem that clear, so I'm just going to draw them out graphically for you. So we imagine this as an axis, where the bottom axis is the size of the input, right? And if we remember, that's kind of our g of n. And we have the time it takes to complete on the top. And that kind of ends up being our O g of n. So, we'll give you an example for case 1 here. Case 1 is that 0. So what does this mean? It means f of n kind of grows slower than g of n. So what does that mean? Well, our f of n might look something like this, right? Constant. And our g of n will look something like this. So it's kind of quick to see right from the beginning that as the size of our input kind of increases, the g of n function here is going to overtake the f of n function. And so when you get a really large size of n, it's going to, take a lot longer for this computation, this algorithm to complete than it would if it were linear. So then we have case 2, and this is the case we're most interested in because a lot of the time when we're determining big O notation, we kind of just want to prove that our algorithm runs in a particular time, right? So this is when they grow at the same rate. So this could be our g of n in this case, and this could be our f of n. And we can see that they kind of grow both linearly, so they have the same kind of rate of growth. And finally, we have our third case here. Well, it's not in blue. Hang on. Oh, blue. Third case might look something like this. It's really just kind of the opposite of the previous case, where this is our f of n, and this is our g of n. And this kind of shows us that our function is going to grow a lot quicker than our expected runtime. So just some quick little example on how this might pan out. If you say had a function f of n being, n squared plus 5, and it's very easy to obviously say, well, this is probably going to grow with this kind of determining factor there of n squared. So we can kind of guess that our g of n is going to be n squared, right? And so when we evaluate our limit, right, it's going to be the limit of the top one, n squared plus 5, our f of n, over our g of n, n squared. And we kind of know we can take this part here and say it's kind of the same as n squared over n squared plus 5 over n squared. And if we simplify this even further, we can say that this is going to be 1 plus 5 over n squared, right? And so now if we take our limit evaluating techniques, we know that, this 1 is going to stay because there's no term of n in it. So as n approaches infinity, it remains constant. And our other term, the 5 over n squared, well, the n squared term is going to get larger and larger and larger, and so eventually this is kind of move towards infinity, right? And we know that 5 over infinity kind of approaches 0. So we can say that the limit of our function just ends up being 1. And from our cases up top, we can see that 1 is a constant term, right? Therefore, we know f of n has O of g of n. So therefore, our f of n in this case was n squared over plus 5, and our g of n was n squared. So we know our function is going to be f of n has O n squared, because our n squared, of course, is g of n. This is just kind of a really quick way to visualize these runtimes. So if we were to kind of graph this one out, it would look something like this. N squared plus 5, so it's going to kind of start up here as our f of n. And we were kind of comparing it against this one, which is going to look like this, right? So we can see that they grow at the same rate, and we know that the difference here is going to be that constant term that was eventually canceled out. So this is just a really quick way to visualize runtime algorithms, and I hope you learned something.